Okay. Hello everyone. Welcome to the post-contest discussion for Codeforces Round 995, Div 3. I hope all of you had good contests. So let's start with the first problem. Let's start with the first problem. The first problem was preparing for Olympiad. Basically, in this we had the story that monocrop and stereocrop are planning for the Olympiad, and there are end days left. And on the ith day, if monocrop plans to practice, he'll solve A of I problems. And if stereocrop plans to practice, he'll solve B of I problems. Now, monocrop can train on any day he wants, but the other guy, the stereocrop, he can only train on some day. So if monocrop trains on ith day, then stereocrop will compulsorily train on I plus 1 day, given that I plus 1 is less than equal to n. Now, monocrop wants to organize his training basically in such a way that he wants to maximize this difference, where M is the number of problems he has solved and S is the number of problems that the second person has solved. And so basically what monocrop wants to do is he wants to solve as many more problems as he can from the other guy. And these were the constraint, like n is the number of test cases up to 10 power 3, n is between 1 to 100, a of I, that is the number of problems that monocrop can solve on one day, are between 1 to 100, and b of I, that's the number of problems that stereocrop can solve, are between 1 to 100. And let's consider the first test case. Okay, let's start with the first test case. So over here the T was 4, so we have like kind of 4 test cases. The first test case said basically we had 2 days in the first test case, and on day 1, monocrop, and this is stereocrop. So on day 1, monocrop could solve 3 problems, and stereocrop could solve 2 problems. And on day 2, uh, M could solve 2 problems, S could solve 1 problem. The condition said that if M solves this problem, then the second person stereograph will compulsorily solve this problem. Like if M solves the problem on day I, that is day 1, then stereograph will solve problem on day I plus 1, that is 1 plus 1, 2. Now what happens if monograph solve problem on day 2? Well, N over here is 2 and 2 plus 1 is 3, which is greater than N. So stereograph won't solve any problem corresponding to this problem. And if you look at the total answer, like if monograph solves this problem 2, then stereograph won't respond by solving any problem. And if monograph solves this problem with number of problems 3, then stereograph will solve this problem with problem 1. Now, if you look at the number of problems by monograph, then he has solved this problem with 3 and 2. So he has solved total 3 plus 2, that is 5 problems. And on stereograph side, he has solved exactly 1 problem. He can't solve.
Can't solve.
Okay. He can't solve any other problem. So basically, you have our answer, that is 5 minus 1, that is 4. And yeah, like 4 is the answer over here. Even if we look at the second test case, there's only 1 day in this test case. Like there's just day 1, and monocrop can solve 5 problems. Stereocrop can solve 8 problems. Now, if monocrop solves this problem, then stereocrop would have solved the problem on day 2. But since there's no day 2, stereocrop won't really solve any other problem. And we just have like the number of problems solved by monocrop is 5. By stereocrop, it's 0. So our answer would become 5 minus 0, that is 5. And we want to maximize this thing. So according to our question, we have to maximize this M minus S value. If we Now, if we look at the third test case, we have 3 days. Here you have monocrab, and here you have the second guy, the stereocrab. On like day one, monocrab can solve 1, 1, 1, and 1 problems, and S can solve 2, 2, and 2 problems. Now, the obvious thing is that monocrabs wants to solve more problems, so he'll obviously pick the last problem because S can not solve any corresponding problem. So your M would be at least 1. Now, plus, what happens if he tries to solve this problem? Well, S would solve this corresponding problem. And like basically, if you look at M and S, that would add a 1 over here, but that would add 2 over here. Someone is on. And like if monocrab just solve the last problem, well, that would lead to 1 minus 0, that is answer of 1. If monocrab solved any of these two problems, like what we would get is one last problem plus one of these problems and one problem over here. Someone's on muted. So basically, we would have m minus s equal to 0 in this case. So we have a better answer where we just solve the last problem, that is problem 1, and s is not able to solve any other problem. So our answer, like the maximum answer, would be 1. And yeah, even in the final test case, we could just work it out in that way. Well, the basic idea is monocrab and this is stereocrab, and you just go to 1, 2, 3, 4, 5. Let's just say that n equal to 5 for now. The last day. Okay, this is the last day, and so if M solves the problem on last day, he'll be the only one to get the points. Like there's no corresponding problem to this problem, like the problem on the last day. So M will at least is going to solve this problem A5. Now, and S is 0. So right now the difference is M minus S is equal to A of 5. That is basically A of n, the last value of A. Now for each of these problems, notice that if A4 solves the, like if M decides to solve problem A4, then S will decide to solve the problem B5. So basically, if M solves A4, then S will solve B5. What will this contribute to our difference M minus S? Well, M is going to solve A4. So like to this M, like it's going to add to plus, like it's going to, A4 is going to be added to M and B5 is going to be added to S. Now, if you look at the difference M minus S, this will basically be like saying that add A4 and subtract B5. Like you're adding A4 to M and you're adding B5 to S. And since there's a like subtraction sign over here, this overall operation would be like adding A4 minus B5 to the overall difference. And you can just quickly see that all of these problems are like independent. All of these pairs are like independent of each other. So if M decides to solve A2, that will only affect B3, that won't affect B4 or B5. And if M decides to solve A1, that will only affect B2. So basically, like for each of the I, so for A5, we know for sure that we are going to solve this thing because this only adds A5 to it. For A4, this is going to add A4 minus B5. For A3, this is going to add A3 minus B4. For A2, this is going to add A2 minus B3. And for A1, this is going to add A1 minus B2. And we can just check if each of these things is like, this can be greater than equal to 0 or this can be less than 0. If this is greater than equal to 0, then we can choose to solve A4. In that case, like we will at best be incrementing our answer. If this is less than 0, then we like won't solve A3, because if we solve A3, then we are basically adding a greater number over there. So yeah, like that was the overall logic. And if you just look at the last test case, so over here we have like n, sorry, n is equal to 6, and our A array, this is our B array. This looks like 8, 2, 5, 6, 2, 6, and this is like 8, 2, 7, 4, 3, 4, 8, 2, 7, 4, 3, 4. Now you can just solve 6 by itself. If you solve 2, you'll get a 4, 2. So you can get like 2 minus 4, which is minus 2. If you solve it 2, this will add minus 2 to our m minus s. So we won't really solve this thing. If you solve this problem 6, S will solve problem 3, and that would add 6 minus 3, which is 3 to our m minus s. So we'll solve this thing, we'll solve this thing, this will give us 6. If you solve 5, S is going to solve 4. So you'll add 5 minus 4 to our m minus s, which is 1. If you solve 2, S is going to solve 7. That's going to add like 2 minus 7 minus 5, and we want to maximize it, so we won't solve this thing. If you solve 8, S is going to solve 2. So that would add 8 minus 2 equal to 6 to our answer. And we want to maximize our answer. So yes, we'll solve it. So overall, if you look at it, what we are actually getting is we're going to solve the last day definitely. Then we are going to solve this 6, which will contribute us 3, 6 minus 3. Then we are going to solve this 5-day problem, like 5 minus 4 is 1. So that would again be our contribution. And we are going to solve problem on day 1. So S is going to, M is going to solve 8, S is going to solve 2. Overall contribution would be 6. We have 6, 7, 9, 10, and overall we have an answer of 16. So this will be the max value of M minus S. And yeah, as you can see. So I don't know, I'm solving the contest and by time seeing. Okay. I don't think there are any answers. Yeah. Right now, let's move on to the code for this problem. Basically, like what we are doing over here is, yeah, this is taking test case, and for each test case, we are calling the solve function. Take the input of n, take input like of both the arrays. Then initially, like the result is our maximum difference m minus s. Initially, what we do is we make m solve the last problem, and there's no corresponding problem for the last problem. Then for each of the problems, starting from like in one best indexing, this is basically like starting from day 2 correspond to I equal to 1, and day n corresponds to I equal to n minus 1. So basically start considering the pairs 0 and 1. What happens if m solves the problem on day 0, and what happens if solves the problem on day 1, 1, 2, 2, 3, and so on and so forth. And basically what we say is, okay, if m solves this problem and s solves this problem, the overall contribution to m minus s difference would be a of I minus 1 minus b of I. And if it's negative, don't do anything, just add the maximum of 0 and whatever this number is. If it's positive, it would be added to rest. If it's negative, it won't affect our result. And finally, we just see out it. Help monocrat determine in the number of sum between them. What is the meaning of this statement? Well, basically, this statement means that, so if we have over here, yeah, right. So 8, 3, 4, 2, and let's just say this is our
Good night. Good night.
so let's just say that these are our arrays. So what our problem says is that on day 1, monocrap can solve 8 problems, and if he solves 8 problems, then S is going to solve 2 problems. Okay, if he solves four problems, S is going to solve three problems. And if he solves six problems, S is not going to solve like any corresponding problems. And what's the total number of problems solved by M? It is, he has solved 8, 4, and 6. So total number of problems solved by M is 8 plus 4 plus 6. What's the total number of problems solved by S? It is 2 plus 3. So this is 18 problems solved by M and 5 problems solved by S. And what we have to do is the difference of these two, like 18 minus 5, which is 13. We have to maximize this value. So over here we could have made one more choice, like rather than solving the 8, 4, 6 problem, we could have just said that I'm going to solve only the problem number 8, and monocrap would solve problem number 2, and we won't be solving any other problems. In that case, monocrap M would have solved 8 problems, S would have solved 2 problems, and M minus S would have been 8 minus 2, which is 6. But obviously, like 13 is greater than 6, so we want to consider the maximum possible value or all such choices that monocrap has. They only want max difference, so why do sum of all differences? Okay, like what we are doing over here is we are considering each difference.
अबे देखो समझना पड़ेगा एक एक क्वेश्चन नहीं 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 आता
So what we are doing over here is we are not considering the max difference in terms of like the difference between these two. So what we are saying is if monocrap solves this problem, then S M solves this problem, then S is going to solve this problem. So what is the contribution of these two problems to our difference? That's what we are considering, not the maximum difference in terms of M minus S. Is there mic on? Okay, like what we are considering is the contribution of these two problems to our final answer and not like each of these individual. So basically, like you could have 8 over here, you could have 2 over here. And if you decide to solve this problem 8, then this would contribute 8 minus 2, 6 to your answer. But if you had 4 over here and 8 over here, if you decided to solve problem 4, then S is going to solve problem 8. Now you are considering M minus S. So 4 is going to add, like this is going to add 4 to M and 8 to S. So you are actually contributing negatively to your answer. So basically, like the answer is the summation of all these contributions over all the possible pairs, which is like I and this I plus 1 pairs. So monocrap M solves the problem on day I and S solves problem on day I plus 1. And if the contribution is negative, we don't consider that day, like we basically don't solve the problem on this day. So that's what we are doing. Okay, till which question we'll be discussing all the questions like up to G. And so that was problem A. Okay. All right. Now let's move to the problem B. Problem B was so let's move to the problem B. In problem B, like again monocrap decided to embark on a long hiking journey, and basically in this hiking journey, what he decided was that he was going to travel n kilometers. On day one, monocrap travels A kilometers. On day two, he travels B kilometers. On day three, travels C kilometer. On day 4, he would again travel A kilometers. On day 5, he will travel B kilometers. On day 6, like he will travel C. Like basically, he's traveling A, B, C number of kilometers each on each like pair of 3 days. And to complete his journey, like monocrap has to walk at least 10 kilometers in total. and we want to determine the day on which he completes his journey. Basically, the minimum number of days that you have to walk to cover a distance of at least n, and all n ABC can be up to n can be up to 10 raised power 9, while ABC would be up to 10 raised power 6, and the number of test cases up to 10 power 4. So like we kind of have to do it in O of 1 or O of n log n time complexity. So let's consider the first test case. In the first test case, we are given n equal to 12, A is 1, B is 5, and C is equal to 3. Okay. Now let's consider what happens on day 1. Monocrap is going to walk A kilometers. So he's going to walk A equal to 1 kilometer. And let's just maintain the total distance traveled. So he has traveled 1 kilometer up to now. On day 2 is going to travel B. On day 2 is going to travel B equal to 5 kilometers. So in total, that's like 5 plus 1, 6. He has traveled 6 kilometers in total. On day 3 is going to travel again like C equal to 3 kilometers. So that's 9 kilometers in total. On day 4, you would again travel A kilometers. So like this pattern would go on repeating A, B, C, A, B, C. So on day 4, you would travel A equal to 1 kilometer. That would be total 10 kilometers. You have to reach 12. Now on day 5, you would travel B equal to 5 kilometers. So that would be 15. And as you could see, like 15 is greater than equal to 12. So Monocrap has completed his journey. So Monocrap has completed his journey on day 5. So the answer would be 5. Yeah. So as you can see, the answer is 5 according to this. And the same process would repeat for all of these problems. Like basically, you just start from day 1, you'd walk A kilometer, you'd walk B kilometer, C kilometer, A, B, C, A, B, C, A, B, C, and you'd keep on doing these things until or like the total cumulative number of kilometers that you have walked becomes equal to or exceeds n. That is, in this case, that was 12. So now if you actually look at now, if the constraints are now talking about the constraints on this problem, like n is up to 10 power 9. So if n was up to 10 power 5 and say like the sum of n over all test cases was bound by some limit, then you could just kind of simulate this whole process. You could walk A kilometers on first day, B kilometers on second day, A, B, C, A, B, C. But the problem is that n is up to 10 power 9. So n is not up to 10 power 5, n is up to 10 power 9, and A, B, C can be up to 10 raised power 6. So in the worst case where A equal to 1, B equal to 1, and C equal to 1, if you try to like by brute force, if you try to simulate it, that would go to big O of n in worst case, and n is up to 10 power 9, so that won't go. So we'd have to figure out some smarter way. Now, if you look at actually what's happening over here is you walk A kilometers, you walk B kilometers, you walk C kilometers, you walk A kilometers, you walk B kilometers, you walk C kilometers, A, B, C, A, B, C, A, B, C. And at the end, somewhere over here, you either walk A kilometer, you either walk B kilometer or C kilometer. Like either your journey ends like A, B, C, A, B, C, A, B, C, and somewhere along this line, the final day, like you walk on day A and your journey ends. Like over here, you have reached the total greater than equal to n condition, or you keep on walking A, B, C, A, B, C, A, B, C, and you walk A, B, and then your journey ends. Your total is greater than equal to n, or you walk ABC, 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 and you have to walk like final ABC, and then your total would become greater than equal to n. Now, the point to be observed over here is that if you consider the last block, like you can basically divide your complete journey into blocks of ABC. like over here too, you can divide it into blocks of A, B, C, and one last like kind of incomplete block. Okay. So you could basically divide these things into blocks of A, B, C, and this last like incomplete block. We'll discuss why we are saying this is an incomplete block. Now, if you have B such blocks, then what is the total distance walked due to these blocks? Well, you would walk A plus B plus C into B, like this is the total distance you're going to walk. And finally, you could either walk A plus B plus C, like this is the last maximum distance you would walk due to the last block. Either A, either just A, just a second. And like this is the distance you would walk due to B blocks, and this is the distance you would walk from the like the last block. This will be A or A plus B or A plus B plus C. Now the thing to notice over here is that since you're walking on the last day, then that implies that this B plus A plus C, like this is less than equal to N. Because if this was greater than equal to N, then you'd have just not walked on the day X. So this is going to be less than equal to N. And then you can just kind of derive what can be the maximum value of this B. So you can just say that B is less than equal to this thing. And you can just like say that since B is going to be an integer, the number of blocks, and B is less than equal to N divided by A plus B plus C. So our total B is going to be less than equal to this floor of N divided by A plus B plus C. You can just kind of say that N is like the maximum value of B, like the blocks. We also have like two B's. So let's just say this is Bn. The number of blocks, the maximum value of the number of blocks is going to be N divided by A plus B plus C. If you have any more than this, then there's a chance that this may exceed X. So after you have like, how many days would it take to walk these many blocks? It would take 3 into blocks number of days, because like each of this consider walking day 1 with A, day 2 with B, day 3 with C. And yeah, like this would be the like after you walk these many blocks, you would be at the end left with some value of N. That is like you have walked these many blocks. This is A
Yes.
plus B plus C into
Then
blocks.
we-
And like you would be at the end left with N modulo A plus B plus C number of days to like kilometers to walk. Okay. Now in the for this remaining part, like N modulo A plus B plus C, this thing is going to be strictly less than A plus B plus C. So you're going to walk at most 3 more days, because once you walk 3 days, you have A plus B plus C number of kilometers, and that's strictly greater than this thing. So after at most 3 days, you're at the end of your journey. So for the remaining 3 days, you can basically simulate the whole process. So the basic idea is we have this N. First, you walk N divided by A plus B plus C into 3 days. That's going to give you N divided by A plus B plus C into A plus B plus C kilometers, and you would be left with N modulo A plus B plus C kilometers. And for this remaining part, you can just simulate the whole process. Logic, yeah, great. And brute force the remaining distance, yes. So, right, that's the overall logic, and like this is the code. First, we take the input N, A, B, C. Then the result, like what is the maximum number of days that we need. So we are going to walk N divided by A plus B plus C into 3 days. Like in each 3 days, we walk A plus B plus C kilometers. And finally, we say N modulo A plus B plus C. So basically, after you walk these many days, N would remain like the remainder of N divided by A plus B plus C. Now, if n is greater than 0, you can walk one more day. And since like you have walked a multiple of 3 days, the next day you would walk 8 kilometers. So if n is greater than 0, increment rest, walk one more day, and decrement from n a. Basically, you have walked 8 kilometers. If n is still greater than 0, you could walk one more day, and that would correspond to subtracting b from n, like you have traveled b kilometers, and incrementing rest, you have walked one more day. If n is still greater than 0, then you walk the final C day and increment rest. Now n, like after all these three loops, n still cannot be greater than 0, because if all these three if statements trigger, then you have walked a plus b plus c days, and n modulo a plus b plus c is strictly less than a plus b plus c. So if after all these three, n is bound to be equal to or less than 0. And finally, we just output our C, that is the number of days we have walked. Okay, now moving on to the next problem, problem C. Yeah. This is preparing for exams. So in this problem, like uh, Monograph was preparing for his first exam, and there were n different questions which could be asked during the exam. The questions were numbered from 1 to n. Now, you had m different list of questions, and each list consists of n minus 1 different questions, n minus 1 different questions. Basically, now each list was characterized by the question which was left out, a of I, which is like this list contains all questions other than this question. So each list was characterized by this question number a of I. So like for example, if n was 4 and you had the question numbers 1, 2, 3, 4, then a of I equal to 3 implies that you had question numbers 1, 2, and 4, and 3 was not present. Now, during the exam, monocrab would receive one of these m question list. So monocrab would be asked one of these m question lists, and what we had to do was basically monocrab knows the answer to these k questions, q1, q2, q of k, and for given m list, we have to determine which of these lists were solvable by monocrab and which were not solvable. A list was called solvable if all the questions in the list could be solved by monocrab. So that was the question, like you're given m list, each with n minus 1 question, and your each list was denoted by the question that's not present in the list. And yeah, like monograph knew answer to k questions where k is less than equal to n, greater than equal to m, and the number of lists is also greater than equal to 1, less than equal to n, basically lies within the range 1 to n. N can be from range 2 to 3 times 10 power 5, and the sum of n over all test cases doesn't exceed 3 into 10 power 5. And like each list is represented by an integer between 1 to n, and the lists are basically given in an increasing order of the question they don't contain, and also the the q of I, the question for which monograph knows the answer. And let's consider the first test case. So in the first test case, we had n equal to 3, n equal to 4, which implies that there are 4 questions. Then we have m equal to 4 once again, like this part, which implies that there are 4 lists, and k equal to 3, which says that 3 questions, like you can solve 3 questions, like 3 questions can be solved. So what we do is, okay, what are the lists that we have? The lists that we have are denoted by 1, 2, 3, and 4. 1 implies that you can the list has all questions other than 1. That is, if you leave out 1, then you have 2, 3, and 4. There are total 4 questions, so our questions are like 1, 2, 3, and 4.
Okay,
If
sure.
if your list is denoted by 2, then that would be like 1, 2 is not present in this list, 3 and 4. If your list is denoted by 3, that would be 1, 2,
TLE.
skip the 3, and 4.
ये
If your
है
list is in,
आज का है, मैं हमको भी दिखा दूँ.
मैं तो इसलिए तो कर रही हूँ.
if your list is denoted by 4, that would be 1, 2, and 3. 4 would be skipped. And what's being said is we know the answer to these 3 questions, that is 1, 3, and 4. So k equal to 3, and the questions that we know answer to are 1, 3, and 4. Now, can the first list be solved? Do we know the answer to question number 2? No, we don't know. So the first list cannot be solved. Do we know the answer? Now talking about second list, do we know the answer to question number 1? Yes. Do we know the answer to question number 3? Yes. Do we know the answer to question number 4? Yes. So the second list can be solved. The third list, do we know the answer to question number 1? Yes. Do we know the answer to question number 2? No. So this cannot be solved. For the fourth one, similarly, like we know the answer to question number 1, but not to 2. So this 2 cannot be solved. So that was the first test case, and let's move on. Like let's take the third test case. Second is very like similar to the first test case. But if you actually look at the third test case, in this case, too, like we were given n equal to 4, and we had m equal to 4 list, basically all corresponding to 1, 2, 3, and 4. That would be 2, 3, and 4. This list 1, 3, and 4. Second list 1, 2, and 4, and 1, 2, 3. Like we had these 4 lists, and in this case, we could solve k equal to 4 questions. Basically, we could solve all the questions 1, 2, 3, and 4. Now, since we can solve all the questions, we can solve all the lists, because like each list consists.
क्लास चल रही है मम्मी.
Like basically, if you could solve 1, 2, 3, 4 all the questions, then any list can contain questions between 1 to n only. So you could solve this question, this question, this list, all the lists could be solved. So the number of lists you could solve was 4 in this case. In the first case, like yeah, basically all lists can be solved. So this would be like 1, 1, 1. In this case, in the first test case, you could only solve the second list. So the answer would be 0, 1, 0, 0. And similarly for the final test case. Now, if you actually work out what's happening, each list has n minus 1 distinct questions. Okay. Now each list has n minus 1, exactly n minus 1 distinct questions. This won't change. Now the question is about k. So the k, the number of questions that you can solve. Now there are 3 conditions. One is that k equal to n. So you can solve all questions. If you can solve all questions, then basically that would imply that you could solve all the lists. Like this is like this condition, like in this condition, you k was 4, so you could solve 1, 2, 3, 4. All the questions could be solved. So if you pick any list 2, 3, 4, can I solve 2? Yes. Can I solve 3? Yes. Can I solve 4? Yes. So if k equal to n, you could solve all the questions, and your answer would be like 1, 1, 1, 1, all ones. The second condition is k is strictly less than n minus 1. So you can solve less than n minus 1 questions. Now, if you can solve less than n minus 1 questions, but each list has exactly n minus 1 distinct questions. Each list has exactly n minus 1 distinct questions, but you can only solve less than k questions, which is strictly less than n minus 1 question. That would imply that each list has at least one question which is not solvable. Like basically each list will have at least one unsolvable question. If I were to take a test case, let's just say that n equal to 4 and k equal to 2, say that you could solve question number 1 and 2. Now, no matter which list you take corresponding to 4, so for example, if you take the list without m, 1, then that would correspond to list 2, 3. You can solve question 1, 2, 1 is not present, you could solve question 2, but you can't solve question 3 and 4. If you take list corresponding to 3, that would be 1, 2, and 4. You can solve question 1, you can solve question 2, but you can never solve question 4. Like you can only solve two questions, and there will always be a third question which you cannot solve. So in this case, like k strictly less than n minus 1. So k equal to n, all list can be solved. If k is less than n minus 1, then no list can be solved. What happens when k equal to n minus 1? Well, you can solve exactly n minus 1 questions. Now, if you can solve exactly n minus 1 questions, basically the questions that you can solve form a list because a list is exactly n minus 1 distinct questions. So the number of questions that you can solve forms a list. So if we look at this problem, like in this problem we could solve 1, 3, and 4, and our n was 4. So this would basically correspond to solving a list because a list will have n minus 1 questions. So if you can solve n minus 1 question, you are actually able to solve exactly one list. Now, what so basically like this would correspond to solving exactly one list if you could solve n minus 1 questions. And what you have to do is just find what is the number of that list, and you can only solve a list with that number. If there's any other n minus 1 questions other than this list, then you won't be able to solve them. So basically, if you could solve exactly n minus 1 questions, say 1, 3, and 4, what you have to do is find the missing question because there are n questions and you could solve n minus 1 question. So there's one question that's missing from this list of questions that you could solve. So find the missing question. Let's just say it's x. And then basically you can solve list x, like list represented by x, and not solve all other list. So that was basically the overall idea of the problem. Like if k equal to n, all solve, like all lists are solved. If k is less than n minus 1, no lists are solved. And if k is equal to n minus 1, exactly one list can be solved among all possible lists. It may happen that that list is not present. So, are there any doubts? First we can do, okay. If there are any doubts, please to put them in the chat. And yeah, like let's move to the code for this problem. So first we take a of I, that is the list representation. So we have nmk. First we input nmk, the number of questions, the number of lists, and the number of questions that we can solve. Then we input the m lists. A of I indicates that the ith list has all questions other than a of I. And then we take q of the k numbers q of I, which indicates that we can solve the ith question. And also according to the question, both of these lists are sorted and unique. So basically q of I is strictly less than q of I plus 1. And again, here we have like our res is vector of int. So basically we had to output m characters or like an binary string of length m, which 0 indicates that the ith list cannot be solved. 1 indicates that ith list can be solved. If k equal to n, you can solve all problems. That basically means that you could solve all the lists. So just set all lists to 1. If k is less than n minus 1, then we don't really need to do anything because by default all vector elements are set to 0. So if k is less than n minus 1, we aren't handling that, like that condition is handled by default. If k is equal to n minus 1, in this case, you could have exactly one list which can be solved. So let's just say that that list is equal to 1. So let's just say that the problem number which is not present in all the problems that we can solve, that's equal to 1. Now notice that all the elements in Q are sorted. So we iterate over all the elements. If the element is equal to our current element, the list number that we are maintaining, we increment this list number, and basically like at the end of this for loop, this would give us the element that's not present in this queue. So if I were to just dry run over it, let's just say that our queue was 1, 2, 3, and 5, and say our n is equal to 5. Now our queue values would be, and let's just say this is our list number. If you actually go over queue, the queue is 1, 2, 3, and 5. And our list number is initially 1, but these two ones match, so 1 would be converted to 2. Then our list number is 2 in this case, these two 2's match, so our 2 would be incremented and converted to 3. Then we have 3 over here, these two 3's match, so that would be converted to 4. And we have 4 over here, 4 and 5 don't match, so this would remain the same. And at the end, our list number would equal to 4. So that would be the element that's not present in the problems that we can solve. And according to the problem definition, this will also equal to the list number of the list that we can solve. So then finally we just iterate over all the lists, and if a of I equal to the list number that we can solve, then we just set res of I equal to 1, and finally just output the res array. Okay, no doubts, I guess. So these were the first 3 problems. Now let's move to the next 4 problems. Let's move to problem D. Problem D was counting pairs. So the problem name was counting pairs. And in this problem, we are given an sequence A of n integers. The ith element of the sequence was equal to A of I, basically an integer array. And we are also given 2 integers, x and y. And so we are also given a definition of an interesting pair. So a pair is considered interesting, a pair ij. If ij are within this range 1 to n, that is, they are basically indices of our array A, and I is not equal to j, like I is strictly less than j. Basically, we are counting all ordered pairs ij, that all unordered pairs ij, number of unordered pairs ij that satisfy this condition that if you remove the ith and the jth element from A, then the sum of remaining elements is at least x and at most y. Like the sum of remaining elements is between x and y. And our task was to determine the number of interesting pairs in the given sequence A. So the constraints for this problem were like t is between 1 to 10 power 4, n is up to like n is from 3 till 2 times 10 power 5. X and Y were like pretty big, up to 2 times 10 power 14. A of I was up from 1 to 10 power 9. And the sum of n overall test cases doesn't exceed 2 times 10 power 5. So big of n or big of n log n solution would work, but you can't have a solution of something like n squared or n. Okay. Now, before going over the test case, like let's just go through the first test case. Then we can discuss a bit about the intuition behind this problem. So according to the first test case, in the first test case, we had n equal to 4, let n equal to 4, let x equal to 8, and y equal to 10. And our array A was the sequence. Let's call it array or sequence. Our array was 4, 6, 3, 6. And what we had said was like these are the 4 pairs. So if you consider removing 1 and 2, like 4 and 6, if you remove 4 and 6, you are left with 3 and 6. Sum of 3 plus 6 is 9. Does 9 lie between x and y? Between 8 and 10? Yes, 9 is greater than equal to 8, less than equal to 10. So this is a valid pair. Then you could remove 1 and 4, like 1 and 4 would correspond to removing 4, 6, 3, 6. That would correspond to removing these two elements. You would be left with 6 and 3. That again has sum of 9. 6 plus 3 is 9. So that would again be valid by the above logic. And then we could remove like 2 and 3. So if you remove 6 and 3, like the elements at 2 and 3, that is 6 and 3, then we would be left with 4 and 6. That would have a sum of 10. 10 lies between 10 is greater than equal to x, which is 8, less than equal to y, which is 10. So yeah, this is also a valid array. And finally, we can just remove like by now 3 and 6, and that would still leave us with 4, 6, which is 10. And 10 is valid because it lies between 8 to 10. An example of invalid pair would be, so for example, let's just say that we decide to remove this index number 2, index number 2 and index number 4. So if we decide to remove index number 2 and index number 4, that would correspond to the remaining array would be 4 and 7, and this would be 7. But 7 is strictly less than 8, so it's not greater than equal to 8, that is our x. So this won't be a valid pair. And yeah, that was the overall like problem statement, and where to find the number of such pairs such that I is strictly less than j. Basically, that correspond to counting them in an unordered fashion. And yeah, like this was the explanation for first sample test case. For the like rest of the 6, it's very similar. Now, before going over them, let's see how we can reduce this problem. Consider what's our like if you remove I and j, if we remove I and j, like basically that corresponds to removing a of I and a of j from a. Now, what would be the sum of a after the removal? Like, what would be the sum of a minus removing this a of I and a of j from a? Well, in that case, your sum would be the sum of a, like what is the total sum of a initially, minus a of I plus a of j. So this would be our new sum, like the new sum of a would be sum of a, the previous sum of a, what is the initial sum of all elements in a, minus you are going to remove a of I and a of j from this array. And what we want is, our problem says that this new sum, this must be between x and y. Okay. Now this is slightly complicated, so let's try to simplify this in terms of a of I plus a of j. So our new sum is equal to like the old sum, the sum of a array a initially minus a of I plus a of j, right? And this should lie between x and y. What we can do is we can subtract this sum of a on all sides. So we can have x minus sum of a greater than equal to sum of a minus sum of a becomes 0. So this would basically be negative a of I plus negative a of j. And we could have y minus sum of a over here. Now we can multiply all these things by -1. That would flip these signs. So this would be like saying sum of a minus x is greater than equal to a of I plus a of j. is greater than equal to sum of a minus y. And let's just say that this is represented by x dash, this is represented by y dash. So in that case, what you have is a of I plus a of j is greater than equal to y dash less than equal to x dash, where x dash is equal to sum a minus x, y dash equal to sum a minus y. All right. So now, like, the overall problem is reduced to finding all pairs which satisfy this inequality, like all pairs ij, I is strictly less than j, that satisfy this inequality, that I and j, the sum of I and j lies in this range y dash to x dash. But got wrong answer in test case 2. Fix one and binary search for next. Okay.
Sir,
Yeah, sure.
uh,
Yes.
can you please tell the average rating of this question, or can you please tell the site from which I can see the rating of this particular question? Actually, I forgot the name of site.
Right. Actually, I am not very sure right now. Yeah, I am. I too don't remember the name of site, but yeah, C list. Right, C list.
Oh, okay. Okay. Thank you.
Yeah, sure. Okay, like right now, what our whole problem has been reduced to is find all pairs between like I to j or ij such that this sum a of I plus a of j is greater than equal to y dash less than equal to x dash. Now, how can we tackle this? And remember, like our n is up to like, I guess 3 times 10 power 5, like 2 times 10 power 5. So if n was like up to 10 power 3, you could have just brute force this, like iterating from I equal to 1 to n and j equal to 1 to n. And we could just check this condition. That would give us a big of n squared solution. But that's not really possible over here. So we have to see something like how can we get these number of pairs. Usually when faced with such problem, like you have O of n squared things to check, but your n only allows you with O of n or O of n log n time complexity in a sense. Now the usual idea is let's try to fix one of these. Let's try to fix A of I. Okay. Let's fix A of I. Like let's fix I. In that case, that would basically mean that you're fixing A of I. Then what can be j, like what can be the value of j? Okay, you're fixed a of I. Now if you consider this equation, a of I is fixed, so the value of a of I is constant, and you can check for value of a of j. Like move this a of I to both of the other sides. Like we are trying to build up constraints on a of j with which we can check a of j. Now if you move these constraints on both the sides, like subtract a of I on all three inequalities, then what you would have is a of j is greater than or equal to y dash minus a of I, x dash minus a of I. Basically, like we are subtracting a of I in all three terms. So basically, your a of j is like you have a range within which a of j can lie. So for this a of I, a of j can lie within this range. Now, if you just try to calculate by iterating over it, like once again, this would give a point you to another O of n squared solution. You can iterate from I equal to 1 to n, iterate from j equal to 1 to n, and j is not equal to I. And for each a of j, you can check whether this a of j lies within this range, like y dash minus a of I to x dash minus a of I. That would give you an O of n squared once again. But there's actually a way to optimize this loop. okay, we can optimize this part of the loop. Like we can't really do a lot about fixing the a of I, because since we are fixing the a of I, we actually have to iterate over all the i's, I equal to 1 to n. But for j, we can actually do something, and that's we can binary search the value of j. Okay. So consider what happens when our array is sorted. Okay, so if our array is sorted, let's just say 1, 2, 3, 5, 6, 7. Okay. I messed up IDK, wasted so much time. Binary search. Okay. So the A of I can be up to 10 power 9. So let's just say that our array is like within this range. And if x dash minus A of I was say 3 and y dash minus A of I, sorry, like you would have y dash on this side, right? So y dash minus A of I was say 3 and x dash minus A of I was say 6. Then our A of j would lie in this range, and that would basically correspond to a certain segment of this array, of this sorted array. Because after this part, like our A of I are strictly less than y minus A of I, and after this part, our A of I are like in this part of the array, your A of j is strictly greater than x dash minus A of I, and in this part of the array, your A of j is strictly less than y dash minus A of I. But it's this part where our equation is satisfied. It's this part where our equation is satisfied. So what we can try to do is there some way to optimally uh, find out what this part is? Well, since like this corresponds to a decreasing, like what we are doing over here is we have this A of j, and if you actually look at the start of our valid array, so 1, 2, 3, 5, 6, and 7. If you actually look at the start of our valid array, starting from 3 and it ends somewhere over here. If you look at it, it's actually the first element which is greater than like the start of our array. This is the first element which is greater than equal to x, sorry, not x, y dash minus A of I. And in C++, like you can either implement your own binary search to do this thing, but in C++, we have a function lower bound where if you pass a sorted array, the begin and end pointer, and if you pass this y dash minus A of I, this would basically give you the first element that's greater than equal to y dash minus A of I. And if you look at the end of the array, so our array was 3, 5, 6. So 1, 2, 3, 5, 6. Now, if you actually look at the end of the array, that is 6, this is the last element, which is less than equal to x dash minus A of I. And if you actually look at 7, so the remainder of the array, which is not a valid A of j, this is the first element, which is strictly greater than x minus A of I, x dash minus A of I. And again, you could use an upper bound in C++ to get this value, like get the pointer to your array in big O of log n using binary search, or you could implement your own binary search to do both of these things. And finally, like what you're doing is, okay, I have this A of I, and so my A of I would define a range y dash minus A of I to x dash minus A of I. And what are all the possible A of j that lie within this range? For this, you do two binary search and get a range of values in your array, say within this range, where A of j lies within this y dash minus A of I to x dash minus A of I range. And there's just one final piece left where you have this condition that I is not equal to j. So you just have to check that if you have this L and if you have this R, if your I lies within this L or R, you have to consider this condition that I is not equal to j, so you kind of have to subtract from over here. Otherwise, like basically with each of these LR, for each of the j in this LR, you can have ij as a pair, assuming that I is less than equal to j. But even if you like basically try to sum of r minus l, you could just divide it by 2 to consider all the pairs. Basically, if you have ij and I is less than j or I is greater than j, then you can at the end just divide by 2 to get all the pairs which are where I is less than j. I mean, yeah, like that's the overall idea. Okay, so don't really think there are any doubts. Let's move to the code for this problem. This is basically we take the test case, number of test case, and solve for each test case. Then first we take the input, the n number of elements in our array, and xy, the range that we want. Then we take all the elements in our array, calculate the sum of our array, that is sum a, current sum. Then update x to x dash, that is sum a minus x, and y to y dash. And then we just sort our array. Next, we iterate over all the elements. Now, we are trying to fix a of I over here. What happens when you try to fix a of I? Well, if you fix a of I, then your a of j must be greater than equal to y minus a of I, like y dash minus a of I. So which will be the first element, which is like the first index, which is going to be greater than equal to y minus a of I. That's going to be the lower bound of y minus a of I. This basically gives you the first element, which is greater than equal to this whatever you pass over here, y minus a of I. And we can just subtract the a dot begin to get this index. Now, what does r indicate? Well, r indicates the first element which is strictly greater than a of I, x minus a of I. So a of j has to be less than equal to x minus a of I, x dash minus a of I. And if you take the first element which is like strictly greater than x dash minus a of I, you're basically getting an r. So your array would start from L, the valid set of all j values. They would start from L and last up to r minus 1. And r would be the basically the first element where this condition is not satisfied. And basically like you would have this for r minus 1 minus l plus 1, that is r minus l elements where this condition is satisfied. So this both these things would be run in big of log n. Like both of these are internal implementations for binary search. And what you're doing over here is basically maximum of 0 or r minus l. So it may happen that r and l end up being same things, or maybe that r minus l can actually never go negative because it's guaranteed that x is less than equal to y, and that basically means that our x dash and y dash will be y dash will be less than equal to x. But just to be safe, like we can just say that r minus l, basically what we do is we add r minus l to our answer. So for this I, we have gotten all the corresponding j, and j can be like j is not necessarily greater than or less than I, but we have just basically got all pairs ij such that a of I plus a of j lies within this x dash to y dash range. Okay, sorry, not x dash to y dash, but y dash to x dash range. And one final thing like we have to deal with is that it may happen that I itself also lies in this range L to R minus 1. So if I also lies in this range L to R minus 1, in that case, we are actually also counting this element I and I, which is not valid according to our problem. So if I also lies in this range, then we just subtract our rest. And finally, we divide by 2. So what we are saying over here is for I equal to 1, say the valid values of j were 2, 3, and 4. For I equal to 2, then say the valid values of j were 1, 2, and 3, and we only considered 1 and 3 out of these because we are cancelling 3. For I equal to 3, let's just say that valid value of j was only 1. For I equal to 4 also, the valid value of j was only 1. Right now, what happens after the complete loop is this adds 3 to our answer, this adds 2 to our answer, this adds 1 to our answer, and this adds 1 to our answer. Now, adding 3 to our answer basically corresponds to 1, 2, 1, 3, and 1, 4. Adding 2 to our answer basically corresponds to 2, 1, and 2, 3. And also, like here, since there's 2, 3, you would also have 3, 2. So this would add 2 to your answer. And adding 2 to your answer would basically correspond to 3, 1, and 3, 2. And this would again correspond to 4, 1. Basically, you see, you have 2, 1 over here, you have 1, 2 over here, you have 2, 1 over here, you have 1, 3 over here, you have 3, 1 over here, you have 1, 4 over here, you have 4, 1 over here, 2, 3, 3, 2. Like basically, each pair ij such that I is strictly less than j is counted twice. Once when I is fixed, and the second time when j is fixed. So each such pair ij, I is strictly less than j is counted twice. So for that, like since it's counted twice, we can just deal with that by dividing or whatever answer we get by 2, and finally we just output this answer. So please, why you did, okay, why did we do rest minus minus? So what can happen is, let's just say that, okay, I can't really find a test case right now, but I hope that you could understand this part, that we are calculating our x dash and y dash. So let's just say that our y dash was 1 and x dash was 4. All right. Now we want all elements ij such that a of I plus a of j is greater than equal to y dash and less than equal to x dash. And according to problem, I cannot be equal to j, like I has to be strictly less than j. And what we are doing over here is, so let's say our array is 2, 2, and 3. Let's say we fix this I, okay, we have fixed this I. Then our a of I is 2, and our y dash is 1, and our x dash is 4. So a of I plus a of j is greater than equal to y dash less than equal to this, and our a of I is equal to 2. So basically that would imply that your a of j is from 1 to 2, that is 1 minus 2, so that would be minus 1, and it's less than equal to 4 minus 2, that is 2. So basically our a of j would lie in the range minus 1 to 2, and by our binary search, like what we would get is, this is the part of the array that corresponds to the valid values of a of j. Like our binary search over here, if you look at our binary search over here, the L and R, like if we perform this binary search in on this array by fixing the value of a of I equal to 2, or L would be over here, or R would be over here. And what we are saying is, okay, let's just add all the corresponding indices, and we would just add R minus L equal to 2 to our answer. But that, what would this R minus L equal to 2 correspond to? Well, that corresponds to taking an index j. So our I is equal to 1, and that would correspond to taking an index j equal to 1 and j equal to 2. So our ij values in this case would be 1, 1 and 1, 2. But we can't have 1, 1. Okay. If our j is equal to I, we can't have that because according to our problem, I is strictly less than j. And we are dealing with j being greater than I by dividing by 2, but we can't deal with I is equal to j. If I is equal to j, we can't have that pair. So what we are saying is, if there's a j in this range L to R, which is equal to I, we are not going to include it in our answer, but just directly adding R minus L to our answer would also add that. Directly adding R minus L to our answer would also add that j. So we are just subtracting our res if there's a, like I lies within this range. Is it managed when we divide our result by 2? I did not sort the array thinking that we needed to maintain the ordering. but a pair like 4, 6 and 6, 4 both are valid. Okay, like according to the question, 4, 6 and 6, 4, 4, 6 is valid, but 6, 4 is not valid. So like you have to maintain the ordering. So basically, if you look according to the question, you have to maintain the ordering if you ask them. But kind of the thing is that if you're counting this pair 1, 2, even if you count 1, 2, and if you count 2, 1, like it doesn't really, you're just counted it twice and you can just divide by 2 to get your answer. And even if you change the ordering of the array, let's just say that your array was initially 1, 2, 3, sorry, 3, 2, 1, and now you made it to 1, 2, 3. Now, the index, if you look at it, the index initially was 1, 2, 3, and the index over here is 3, 2, 1. But even if you consider these two indices, like if you just go by the index of the modified index, I dash 1, 2, 3, if you're going to count this 1, 2 once, then you're actually counting this 2, 3, 2 once. So basically, like you have 3, 2 over here, but according to your question, you can just flip it to 2, 3. Basically, like where do we subtract by a dot begin? We subtract by a dot begin because this lower bound basically gives us a pointer to the first element that's greater than this y minus a of I. Okay, I think my mouse is not working. Just a second. Okay. Like basically the reason why we subtract by a dot begin is we are actually given a pointer to the lower bound rather than having an index. So we just say that this pointer minus this a dot begin, this will give us the index of a dot l. Yeah, like that's how you do it. Just a second. Again. Chrome has crashed. Just a second. Oh. Oh, you're right. This is not actually Mac, it's Fedora, so yeah, it crashes pretty often. And that was like the problem D. And if you have any doubts, to put them in the chat. So about why, yeah, any doubts?
Is there any approach rather than binary search of
So any other approach other than binary search? Like it would be difficult to consider approach other than binary search because we kind of have to, if you look at the crux of the problem, it just boils down to counting the number of pairs a of I plus a of j uh, that satisfy this inequality.
if
Now,
we
if
use
Yeah.
If you use map for finding the files, like if you fix A of I and if you check the range of A of J in their frames, is there any like
If we
if it
check
works
the range of A of J in,
in the range of X dash and Y dash?
you fix A of I. Like so if you had some like better constraints on A of I, like A of I between 1 to 10 power 5, then you could do something like a prefix array and basically like okay, your answer you could just say that prefix between x dash minus prefix between y dash minus 1, but your A of I is up to 10 power 9 over here. So in one way or other, you actually need binary search about like fixing A of I. The problem is that the moment you fix A of I, okay, so the moment you fix A of I, what you get is you get a new range for A of J. And like as far as I know, if you are getting different like set of ranges, if you're getting a different set of LR in each query, like basically this is a set of queries on an sorted array. If you're getting a different LR and if your A of I is up to 10 power 9, I don't really know of any approach where you won't use binary search and do it. If your A of I was say up to 10 power 5, what you could do is you could create a frequency array and then basically calculate the prefix for this frequency array. And then you could say that between L to R, the number of elements that lie between L to R is prefix of R minus prefix of L minus 1. But since over here, like your LR can be up to 10 power 5, that would be difficult. So just learn binary search. Yeah, like binary search is pretty important, especially in like div 2D. So, right, like that was overall problem D. That was okay. Any more doubts for problem D? Okay. I think we can move to problem E. Just a second. And we can have problem E. All right. Now, in problem E, what we were given is like we had a story like a batch of Christmas trees have arrived in largest store in Berlin, and you have n customers who want to buy them. And basically, like you could fix the price for one tree, basically the price of the trees, and each tree would be sold compulsorily for that price. Now, each customer had two corresponding integers, A of I and B of I, and they were known. So you have these two arrays, A and B. And what you do is, if you fix the price, and if the price is less than equal to A of I, that is at most A of I, then that customer will buy that tree and he would leave a positive review. Positive review don't really affect this problem any much. But if the price is greater than A of I, and but if it's less than equal to B of I, the customer would still buy the tree, but he would leave a negative review for the like purchase. And if the price is strictly greater than B of I, the customer would not buy the tree and he won't really leave any reviews. So, and our task was to calculate the maximum possible earnings that the store could get, given that you can receive at most K negative reviews. So you cannot receive more than K negative reviews. And the constraints were T was up to like number of test cases was up to 10 power 4. The number of customers N was up to 2 times 10 power 5. Even summed over all test cases for up to N times 2 times 10 power 5. And the negative review that max negative review was from 0 to N. And our A of I was from 1 to 2 times 10 power 9. B of I 2 was from 1 to 2 times 10 power 9. And we were given that A of I is strictly less than B of I, meaning that the price where the customer will buy giving positive review was less than the price, like the max price where customer would buy giving negative review. Can we do binary search on answer in E? Well, okay, like first let's discuss what we are actually doing over here. And first let's go through one of these test cases. So if you consider the first test case, over here we had n equal to 2, so you have two customers, and the max negative rating that you can get is 0, so you can't have any negative rating. A of I is 2 and 1, B, like the array B is 3 and 4. What this means is, if your price is becomes like greater than equal to, if your price is less than equal to 2, okay, just say, okay, let's consider the first customer. Okay, what first customer says is he has A of I equal to 2, so this means that if the price is less than equal to 2, then the first customer buys it and he leaves a positive review. If the price is greater than 2 and less than equal to 3, you will buy it and leave a negative review. If the price is strictly greater than 3, then he would not buy it. Like this customer won't buy your tree. And the price of tree will be same for all customers. So if you fix the price of tree to be 2, then both the customers will be offered a price of 2 and they will decide would they whether they want to buy it or not, and if they are buying it, are they going to leave a positive or negative review. And basically like over here you could have 0 negative reviews. So like similarly for the second customer you would have CA is 2, 1 and 3, 4. So similarly for the second customer, if the price is up to 1, like 0 or 1, in that case you will buy with a positive review. If it's between 2 to 4, then you would buy with a negative review. Now in this case you couldn't have a negative review because the max number of negative reviews was 0, so you don't really have the choice for negative review. The first customer would have negative review in the range 3 to 3. The second customer would have negative reviews in the range 2 to 4. Basically, this implies that you can't have prices between the range 2 to 4. So the only possible choices for price was 1 or 5 or greater. Now, if you have 5 or greater, then none of these customers would actually buy your product because 5 is greater than 3 and 5 is also greater than 4. So no one would buy. So for 5, your profit or your sales would be 0. For 1, customer 1 would leave positive review, customer 2 would leave positive review because 1 is less than equal to 1, 1 is less than equal to 2, and both of them will buy it. So basically you have 2 as your profit. So that was the first case. If you look at the second case, greedy thought comes by practice. How to observe this. Okay, like we'll discuss what happens. And for the second case, like you had A of I equal to 2, like there's just one customer, and B of I equal to 5. And you could have like one negative review at most. So since you can tolerate one negative review, you could have price of 1, 2, and you would have like only positive reviews. When your price becomes 3, it's greater than 2 but less than equal to 5, so still buy but negative review. 4 still buy but negative review. 5 still buy but negative review. 6 won't buy, like the customer won't buy from 6. So 5 is the maximum that you can raise your price, and that would basically lead you to like the maximum profit you could earn is 5. 5 in this case, and these test case below are like similar. Now, can we do binary search on answer? Okay, like now, if you actually look at this problem, the first thing that would strike you that maybe you can do binary search on answer on this question. There are a few problems when you look at the binary search solution. So the most obvious candidate for binary search would be profit, right? Like the profit or the sales that you're doing. Let's just say your price is P, okay? Uh, your price is P, all right? Okay, no, sorry, like you would want to maximize your sales, you want to maximize this, and you would binary search on P. Okay, and let's just say that your price is P. So how many people buy? Like the number of people who buy your product, how many people actually buy your product? Well, that's actually equal to the number of B of I, like the number of places where your P is less than equal to B of I. Because A of I is strictly less than B of I according to our question. And if your price is less than equal to B of I, the customer is going to buy that product. If it's greater than B of I, he's not going to buy that product. He may give negative or positive review, but he's going to buy the product if your price is less than equal to B of I. How many negative reviews are you going to get? Well, your negative reviews is equal to the number of products where your price is greater than the number of customers for whom this price is greater than A of I. So they are not going to give a positive review, but it's still less than equal to B of I. So they are going to buy the product and give a negative review. So if the question had no negative review part, if you didn't have this negative review part, then you will actually see that the number of people who actually buy your product, uh, as you increase your price, the number of people who buy your product actually decreases at price zero. All of them will buy. Somewhere over here, you would maybe like decrease the number of people who would buy your product would decrease. It would go on decreasing, decreasing, decreasing up till like somewhere like the max B of I. From where onwards, no one would buy your product. And your profit, like your profit for P, your profit or your sales that you want to maximize. Actually, what I have this said in your profit? Find the max. Okay, earnings. Let's just say sales for now. Your sales for a price of P is actually P into the number of people who buy your product. Okay, the number of people who buy your product. Now you could kind of see that maybe you could reduce this to ternary search, and it would be a bit difficult to see still. And if you actually add on to that the condition that the negative review has to be less than equal to k, then it becomes very difficult to binary search on this thing. Because I mean, to begin with, while the number of people who are buying your product, this is like monotonically decreasing, like it's non-increasing basically. So you can binary search on certain number of people who buy your product, but the sales, that is P into number of people who buy your product, that actually looks something like this. So maybe you could ternary search on this. I'm not sure if you could ternary search on this, but when you go on and add this condition that the number of negative reviews that you get has to be less than equal to k, then this whole thing becomes even more difficult. And binary searching, I don't know if it's possible, but even if it would become very difficult. So it's not monotonic because we have choice to keep. Yeah, like it won't be monotonic, but just that non-increasing. Okay. You saw a few people doing binary search. So I'm not sure what are the variables they picked for binary search. Maybe it's possible, but let's try to see like what are the things that you need to get to, let's just say, so if you have this price, if you're selling your trees at a price of P, okay, you can calculate the number of people who are going to buy your trees. Basically, that's the number of P I where P is less than equal to B of I. And you can calculate your negative review, the total negative review that you're going to get. That's basically your P where P is greater than A of I but less than equal to B of I. Now look, if you have these two things, you can know that if your negative review is less than equal to K, in that case your sales is going to be what P into the number of people who are buying this thing, like the number of people who are buying the tree. Okay, since since this many people buy the tree and each tree is sold for P price of P, then your total sales would be P into number of buy. Now, basically, these two variables, if you have your P, let's just say that you haven't decided your P, but if you actually look at it, these two variables decide, along with P, decide what your sales will be. Now, for say P equal to 6, your num by and your num like negative reviews, if they were say 4 and 3, for P equal to 7, they still remain 4 and 3. For P equal to 8, they still remain 4 and 3. And then for P equal to 9, let's just say something changed and less number of people decided to buy this thing, and that was also reflected over here. If you actually look at it, you don't really need to consider P equal to 6 or P equal to 7. We just directly need to consider the maximum P for one set of these number of buy and negative reviews. Why? Because your answer is P into num by, and given that your negative reviews is less than equal to K, if it's greater than K, then it's kind of 0 or -1. But like you don't have to consider that case where it's greater than K. But if neg reviews is less than equal to K, then your P into num by, basically this increases as P increases. So if P increases and your like num by and neg review is fixed, and let's just say that neg review is less than equal to K, in that case, your sales or your revenue increases, and we want to maximize this thing. So rather than trying to see what are the like trying to iterate over all the possible values of P, which would be like very large, let's see what are the different values that this num by and what do we have, neg reviews can take. Okay. I'll just rejoin in a minute. Is my voice audible? Okay, I think my screen froze and I've exited. I'll just rejoin in a minute. Okay. Okay. Screen. Yeah, right. Guess we were on problem E. Right, yeah. Right. So like okay. I hope I'm audible and you can see my screen. Yeah, sure. Now, like based on what we discussed up to now, if you have a price P and you know the number of people who are going to buy this thing and number of negative reviews you are going to get. Basically, this is just to check if this whole thing is valid, and your P into number is your sales, and this thing increases once your P increases, assuming that this number is fixed. Number is fixed. Now, the values that your P, the price can take is very large, like very large range of values. Like your price can take a large range of values. So rather than that, let's try to see what are all the set of values that your numby or neg review can take, like the number of negative reviews and the number of people who are buying the product. Okay. And if you can buy this product, let's just say numby and neg review is fixed in a range of price, say L to R, then you would always consider the maximum price for which this pair occurs, because you want to basically increase your sales as much as possible, and they are increased when you increase the value of P. So that's the overall idea behind this problem. Like this pair, you can't really fix, like you can't really iterate over all the prices that you can have because there's a huge number of prices. But rather than that, you have this pair for each price. If you actually look at how you're determining the price of the trees that are sold for each P, you're actually first calculating this pair. So rather than trying to fix P and iterating over P, let's try to see, can we somehow fix these numby and neg reviews or iterate over all the possible values that this pair can take on. So that's the basic like idea behind the overall optimization. Because I mean, if you actually look at P can be between 0 to 10 power 9. 0 meaning that you sell the trees for practically free, and 10 power 9 because if uh, P exceeds 10 power 9, it's going to exceed B of I and no one's going to buy anything. But iterating overall 0 to 10 power 9 is not really a feasible solution. Okay. Now we want to iterate or like, or we want to see what are the different values that this pair can take. Okay. Let's consider the first case. P is 0. We are basically offering, like, consider the start of this range. P is 0. We are basically offering trees for free. Well, since our A of I is greater than or equal to 1, less than or equal to 10 power 9, and B of I is obviously greater than A of I. A of I is greater than or equal to 1, your price is 0. This means that everyone is going to buy the tree. So you have N, like everyone's going to buy the tree. And the number of negative reviews that you are going to get is 0. Like everyone's going to buy the tree, and P0 is less than or equal to A of I. So everyone's going to give you a positive review. Now, what's the next point where a change occurs? Okay, let's just say that you had A of I, the array A equal to 2. Let's just take the first test case actually, 2, 1, and 3, 4. Okay, 2, 1, and B is equal to 3 and 4. What happens when you increase the price to 1? Well, this pair, the number of buy and the number of negative reviews remains the same because there's nothing new happening. The P is still less than equal to A of I for all of them, and like there's no change basically over here. What happens when you set P equal to 2? Well, when you set P equal to 2, P equal to 1 didn't exceed this part. So over here, P equal to 1 didn't exceed this part, but P equal to 2 exceeds this part. So P equal to 2, 2 is greater than this A of I, that is A of 2, which is equal to 1. So there's going to be a change. Now this customer is still going to buy the tree because 2 is still less than 4, but is going to give you a negative review. So the number of trees you buy, basically n equal to 2 over here, is still going to be 2, but the number of negative reviews that you are going to get has increased to 1. Okay, what happens when you make P equal to 3? Again, this customer is still going to buy your trees, but when you make P equal to 3, but now like up to 2 he was buying with positive review, but now he's going to buy with a negative review. So you basically have 2 2. For now, forget about all the constraints and everything. We are just seeing what are the different possible values that this pair is going to have. Next, if you actually look what happens next, what happens when we do P equal to 4? Well, there's this customer is actually having a problem because when you have P equal to 4, that exceeds the value of B of I, that's 3. And he's going to stop buying your trees. And in that case, you'd basically, one customer would be lost. So only one tree would be sold, and that customer would also stop giving you negative reviews. And when P equal to 5, you're exceeding this 4. And yeah, like when P equal to 5, no one's basically going to buy you a tree and no one's going to give you a negative review. Now, if you actually observe these transitions, like if you observe the changes that are occurring, change occurs in this pair, like your num by and the negative review. This pair only changes like the first time, like the time when P exceeds something. If P exceeds something, so if P exceeds A of I, basically if P becomes equal to A of I plus 1, then that would imply that your negative review, like one customer would still buy that tree, but your negative review would increase by 1. If P exceeds B of I, if P becomes B of I plus 1 for some customer, then the number of buyers, like one tree would be like that customer would stop buying your tree and you'd have one less buyer. And at the same time, that customer would also stop giving you negative reviews. So you would have one less negative review. Basically, if you actually look at it, what this is saying is that if you have some number of buyers and some number of reviews up starting from over here, so you had these many buyers and these many reviews, say X number of buyers, and like let X represent this pair, and it changed, like it remained same, remained same, remained same, remained same over here, and it changed over here at point Y at price equal to Y, then this Y is going to be either A of I plus 1 or B of I plus 1. Like, and the previous number by definition would be A of I or B of I. Basically, what this is implying is that this pair, number of buy and the number of negative reviews, is only changing when your price becomes A of I plus 1 or B of I plus 1 somewhere or other. And basically, like if you actually start with the number of buyers being n and the number of negative reviews being 0, and you just continue, somewhere over here your like the first A of I would be exceeded. You would have first A of I over here, and your first A of I would be exceeded somewhere over here. Number of buyers would remain the same, but one buyer would start giving you negative reviews. Maybe you exceed one more A of I over here. Number of buyers would remain same, but one more buyer would give you negative review. So this is A of I, and this would be A of I plus 1. Same over here. And let's just say some more over here you exceeded one of the B of I's. So starting from here, that is B of I plus 1, one of your buyers has been reduced and one of your negative reviewers has also been reduced. So basically, if you look at it, these A of I and B of I, they are the critical points where this pair, the number of buys and the number of negative reviews, is changing. So the number of buys and the number of negative reviews is only going to change when your price is like A of I plus 1 or of the form B of I plus 1. So up to A of I, this would remain same, and at A of I plus 1, starting from A of I plus 1 and ahead, it would change to something else. So that was the basic idea behind this problem. And what you can do is basically just kind of take all the A of I's and B of I's. Now, what would exceeding A of I do? So what happens when you exceed A of I? You're increasing your negative reviews. Like the customer would still buy your tree, but he is going to give you a negative review. What happens when you exceed B of I? So you're buying, the price was between A of I and less than equal to B of I up to this point, and now it has exceeded. So in this case, like you are decreasing your number of buyers, and at the same time, that buyer is no longer going to give you negative review. Right. Any doubts? So, yes, no. All right. So I think we can move to the code for this problem. And if you actually look at the code, this is again taking the test cases, and for each test case, we take n and k, the number of buyers and the maximum negative review that we can have. And we input both the arrays A and B. Then initially we just set max profit to 0. That basically implies no tree is sold or all trees are sold at cost of 0. When you have cost of 0, basically all trees are sold and no one gives you a negative rating. So let's just start with this thing. And what we do is we iterate over all the A of I. What happens, what is the change that's going to happen in our pair, number of buyers and the negative rating, when your price exceeds A of I? When our price exceeds A of I, one customer is like the customer I is still going to buy the tree, but he is going to give a negative rating. So basically the difference in negative rating, the negative rating is going to increase. Then we iterate over all the B and see what is going to happen when price exceeds B of I. That customer is going to stop buying the trees, so number of buyers is going to decrease, and that customer is also going to stop giving us negative rating, so the negative rating decreases. And what we do is basically just go on iterating all the price and rating in the diff neg rating. Why the diff neg rating? Because the diff neg rating is updated for all the critical points, like it's also updated for A of I and it's also updated for B of I. So it would basically contain all the critical points, unlike the diff num bias. And for each of these prices, like up to this price, this max number of buys and the negative rating would be maintained. And when we cross this price, then we would have a change in our negative rating and number of buyers for our trees. So when we cross this price, our negative rating and number of buys would be changed by this difference that we have calculated above over here. And up to this price, like we had this number of buyers and this negative rating. If this negative rating is less than equal to k, then since this is the maximum price where this pair remains constant, and as we know, we want to maximize our profit or the sales, what we can say is our maximum profit is maximum of what it already is versus the price into the number of buyers who are buying the trees at this pair. And finally, we just output our max profit. And if you actually look at where this whole thing goes from, this starts from all trees being sold and zero negative rating. And this would just like go on to some critical point. You would have entries sold one negative rating, entries sold two negative rating, or somewhere here you could have n minus one negative rating. And at the end, it would end when zero trees are sold and zero negative ratings are given. So that would be like the end of the whole loop. So you are basically iterating over all the possible set of pairs of number of buyers and the negative ratings. And on basis of that, we are just seeing the maximum price for where each of these pairs occur and calculating the sales for that pair. So yeah, right. Let's move to the next problem. That's problem F. Problem F. So the problem F was named Joker, and in this problem we had a deck of n cards. The positions in the deck are numbered 1 to n from top to bottom, and a Joker card was located at position M initially. And we had Q operations which were applied sequentially to the deck. So basically these operations were persistent. Once you perform the operation, the deck was changed and it would remain changed for the next operation. And during the ith operation, we are given an integer a of I. And what we can do is we can take the card that's at the position a of I and either move it to the beginning of the deck or at the end of the deck. Basically, our deck is represented by an array and say our a of I is 2. So 2 and 1. So this element, we can take this element, remove it from here. Like we take this element and remove it from here. And we either add this one to the start of the array or to the end of the array. This is the operation and we are given a of I in a particular order. And our task was to calculate like the number of distinct positions where the Joker could have been after each of the operations. So let's consider the first sample test case. Now in this test case, you had n equal to 4. So you had a deck of, no, not 4, but 6, n equal to 6. So in this case, you had a deck of 6 cards. Let's say number them 1, 2, 3, 4, 5, and 6. And m equal to 5. So m equal to 5 indicates that the fifth card is a joker. So basically this card is the J card, the joker card. And we had 3 queries. The first query said that we could take operate on the card 1. Now, if you say operate on card 1, you have 1, 2, 3, 4, 5, and 6. There are 2 things you could do with card 1. Take the card 1 and insert it at the first position. That's basically where it already is. 1, 2, 3, 4, 5, and 6. Or insert it at the last position. Take the first card, like card 1, and insert it at last position. That would do it 2, 3, 4, 5, 6, and 1. Now, if you look at the position of the joker card, like the joker card is the fifth card. Over here, its index is like 0-based indexing 0, 1, 2, 3, and 4. Over here, its index is 0, 1, 2, and 3. So you have 3 different positions for your joker card depending on what you did with this operation, card 1. And so the first number would be 2, basically. First number 2 indicating that like you have 2 distinct positions. And then after this, like the next query said that, okay, you can operate on 2 now. Now what happens when you try to operate on 2? Well, for 1, 2, 3, this would either become 2, 1, 3, 4, 5, 6, or this would become 1, 3, 4, 5, 6. In either case, the answer would be either like the index would be either 3 or 4. And over here, once you operate on 2, this can remain as it is. 2, 3, 4, 5, 6, and 1. Or the 2 can go to the end of array, that is 3, 4, 5, 6, 1, and 2. And in this case, like the index would be 0, 1, 2, and 3. And in this case, it would be 0, 1, and 2. So you have 3 possible distinct indices for 5. Either it's 2, or it's 3, or it's 4. And our answer is 3. Like basically 3 possible different set of indices, 2, 3, or 4. So yeah, right. 2, 3, and 4. So 3 possible set of indices, and the answer would be like 3. And finally, if you perform the third operation, like if you operate on 3, you would get much more possible set of indices, and your answer would be 5 in that case. if required, like you could work out through this example. And a big problem in this thing was that the constraints for this problem. So n was up to 10 power 9, and m was like m, the index of the joker was from 1 to m, the initial index of the joker, and the number of queries were 2 times 10 power 5, and the sum of queries over all test cases was like bounded by 2 times 10 power 5. So basically, this constraint mean that you can't really do something that has, like, you can't really operate on the array in big of, even in a big of n sense. So there's really no way to operate on the array in big of n sense. You can't really also do much with m, like basically you can just maintain it as indices, and most of it has to do with maintaining, like dealing with how do you deal with this each of these queries separately. Like there's not really much of pre-processing that you can do because of these constraints. Okay, now let's consider what's happening over here. All right, initially you had 1, 2, 3, 4, and 5 and 6. Okay, then you operated on 1. Now, since you want the number of possible values, like the number of possible indices of I, the number of possible indices of Joker, it's always a good idea that when you have n to be very big number, like up to 10 power 9, and you want to have like all the possible set of values in this range, like 1 to n, and it's always a good idea to kind of maintain the ranges, because usually with such operations, the ranges increase rather than like randomly opening up indices. The indices open up in form of ranges. So let's just, rather than saying that the joker is at 5, say that the joker can lie in the range 5 to 5. All right. And what happens when you operate on 1? Okay. And we are using 1 based indexing over here. So just to be like safe, for easier understanding, not safe, like for easier understanding, we'll just use 1 based indexing. What happens when we operate on 1? Okay, there are two things that you can do when you operate on 1. Just take it and put wherever it is. Like take it and put it at the start of array, but it's start of array already, so nothing changes. So 1, 2, 3, 4, 5, and 6. So starting from 5 to 5, it went to 5 to 5. Like nothing changed over here. The other thing is put it at the end of the array. Okay, 2, 3, 4, 5, 6, and take this 1. You're operating on 1. Take this 1 and put it at the end of the array. Well, when you put it at the end of the array, the index of your joker actually decreased. So the index decreased, and now your index became 4. So your range of 5 to 5 actually reduced to range of uh, 4 to 5, increased to range of 4 to 5. So you have two possible set of values. All right. What would have happened if you had operated on 6? Say 1, 2, 3, 4, 5, and 6, and this is your joker. All right. What happens when you operate on 6? When you operate on 6, you can remove this 6 and either put it at the end of array, which is where it's already is. Then your 5 to 5, like your joker wouldn't really move in that case. It would remain at 5. But you could do one more thing, and you could put this 6 at the start of array. In this case, like this would be 6, 1, 2, 3, 4, 5. In this case, your joker actually moved to the right. So your 5 to 5, after operating on 6, this becomes 5 to 6. In fact, even if you had an array of, let's just say, length 10 and 5 was your joker, 5, this is where your joker is. Even if you operated on, say, some number 8, you have two options. When you operate on 8, you either put it at the end of the array. This won't change the index of my joker. So index of your joker is, say, 5 to 5. If you operate on 8, this won't change the index of your joker because it would remain where it is. Or you could put it at the start of the array. This will mean that this part will have one extra element, And in that case, like your index would be incremented by 1. So this is 5 and this would move to right. So your index would move to right basically. Basically what we are saying over here is if you lie in LR and if you're operating on say index I, if I is strictly less than L, then your LR would get converted to L minus 1 R because your joker can lie in range L to R and you are removing this element I over here. So this whole L thing will shift to the right. Or you can also keep the element I to at the front and nothing would change. Or you could push the element I to the back and that would basically push this whole range to the left. So LR would be maintained and this would open up one more index that is L minus 1. And if your index I is like greater than R, in this case, your joker can be in this possible range. So this is your complete array. Your joker is in this possible range L to R. And over here you have this I. You can either push it to the end of array. In that case, L to R remains same. Or you can take it and put it at the start of the array. In this case, that would basically correspond to pushing this whole thing, like shifting every card by one place to right. So your LR would get converted to L and R plus 1. Like that's the overall idea from 4 to 6. 4 to 6, I don't really get what you're trying to say over here. Four to six. Okay, I don't really get. Okay, no, just answered your question. All right. So yeah, like basically that's the point. If your I is less than L or like I is greater than R, what happens when the I and basically like we are maintaining the range of values that your joker can take, and yeah, that's the thing we are maintaining, and we can see later like how can we calculate all the ranges where all the possible number of values where the joker can be. What happens when this I is less than equal to greater than equal to L and less than equal to R? Well, that's where you have a slight problem because basically if you look at I, what I is doing is when you operate on I, this is basically pulling all the elements if you push it like if you put it at the end of the stack. This is basically pulling all the elements to its right to the left, like shifting all the elements that are right of it one place left. Or if it's over here and if you're putting it at the start of the array, then this would basically shift all these elements to right by one place. What happens when you have I that is between L and R? Well, if it's between L and R, no matter what you do, your LR won't really change by much. Okay. Like Joker can be in any of these possible places. If you put your I, if you put this box I over here, then this L would shift, but this R would remain constant. And if you put your box I over here, this R would shift, but this part would remain constant. So LR won't really change if your I is between L and R. But that's one thing. What happens if the box that you are operating on, if the card that you're operating on is itself Joker? What happens when you're operating on the Joker itself? When you're operating on the Joker, you're actually opening up, like you're actually creating a new range. You could either put the Joker at the start of the array, that corresponds to this new range 1 1, or you can put the Joker at the end of the array that corresponds to starting a new range n. And on each of the next operations, on each of the further operations, you could go on like kind of expanding both of these ranges. And basically, if you observed up to now, all the ranges are expanding one place at a time, like either from LR to you can go to L minus 1 R or LR plus 1. you're expanding one place at a time. So basically you could like a normal operation would something look like initially you are over here at M to M, then some after some operations you go from something like L to R, and then you get a chance to do an operation over here in between. LR won't really change, but you have actually opened up two new ranges. LR won't really change, but you have opened up two new ranges, that is 1 to 1, and a new range over here, that is N to N. Now your joker can be anywhere in this range LR, because basically if it was over here, then you could just have it in such a way that your joker could be in this range LR, or if your joker was exactly present at the point where the operation occurred, then it could be at a range in the range 1 to 1 or N to N. And then for each of the further operations, you could just go on expanding all these three ranges. Like if this index lies over here, then you could just pull the L this side, pull this one this side. If the I lies over here, you could pull this R to its right, pull this N to its left, and basically expand all these three ranges. And there's one more thing, like a slight edge case that you have to deal with. What happens if the joker is at this point M, like exactly at this point M, and the point M is being operated on? Well, if it was between points say M minus 1 and M plus 1, and it was being operated on at point 1, the M could go to front or back, and you also had one more possibility that the joker was at M minus 1, so it would come at M, or it was at M plus 1 and it would come at M. So your range LR would be maintained in case it was M minus 1 and M plus 1. But in case the joker was in this range M to M, in this case, basically you have this exactly one card, and this is going to move either to 1 to 1, or this is going to move to N to N. And these are going to be your new ranges, and nothing would remain over here. So this was like one slight edge case that you had to deal with. And basically, like, to solve this overall problem, you start with this range M to M, gore all the queries, iterate all the ranges that you have, see if this like I is less than L, or this I is greater than R, or if this I is lies between L and R. And based on what we have discussed, like basically you can expand this range. In this case, the range would become L minus 1 R. In this case, the range would become LR plus 1. And in this case, depending on what like LRR, it would either become this, or it would either become this plus LR. So that's the overall idea. And finally, once you're done with all this, you could merge ranges. For example, it may happen that you started with ranges of this form, and after doing some operation, like you did some operation with I equal to 3, then that would basically give you 3 4, and for actually let's just say this is 2, and that would lead to 1 2 over here becoming 1 3, 5 7 over here becoming 4 7. And then finally what you could do is you could just merge all these ranges and say that, and also you would get 1 1 and then say 7 7. And what you could do at the end is just merge all these ranges to keep it simple to basically handle. So 1 to 3, 3 to 4, 4 to 7, 1 to 1, and 7 to 7. If you merge all these ranges to the smallest possible range, that would give us 1 to 7. So basically what we can do is, if you actually observe what's happening over here, is there are only three possible set of ranges where the joker can be. One is a range centered at M, somewhere over here. Other is a range starting from 1 and somewhere up to this L dash. And the final one is a range ending at N and starting somewhere at say R dash. And it may happen that at some point both of these ranges meet, or maybe even all three of these ranges meet. So that's also a possibility. But at any point you have at max these three ranges, because this range expands this way, this expands this way. and like these would be the only three ranges. What we can do is iterate over all queries, update our ranges, then merge them to remove like duplicate ranges, and finally, like once we have these ranges, how many jokers, like how many positions are there for the joker? There are L dash minus 1 plus 1. How many positions are there for the joker in this range? There are R minus L plus 1. And similarly, basically R minus L plus 1 kind of things, or all the possible ranges. That would be how we can get answer. Will the difficulty be above 1900? Uh, Not sure exactly. I mean, it kind of could be div 2D usually. So, okay, hung up. So yeah, like this was my implementation for this. I mean, there are better ways to implement it where you could maybe have a Boolean variable. Do I have a range starting from front? Do I have a range starting from behind? But basically, what I did was during the contest, maintain this ranges variable and uh, initially just push back m to m. So initially my joker is between m to m. Then for each of the indices, like for each of the query, we take the index that is given where we are going to operate and kind of apply this index to the current set of ranges that we have. What does this apply does? If I go to apply, yeah, like here's the apply. What this apply does is it first we initialize a new set of ranges and we iterate over all the LRs that we have. There are two conditions. The simpler conditions are that if index lies out of L to the left of L, it would basically shift the whole LR to left by one place if you could push the index to the end of array, and that would basically increase your L LR by one place to the left. That will be L minus 1R. If the index lies to the right of R, in that case, that would basically push the whole thing to the right. So that would become L to R plus 1. And if it lies in between, like as we discussed, if there's something other than like if it's just M and M, in that case, like index would equal to L and index would equal to R. And like in that case, we can't really do anything if the index is only equal to M and M, then the whole M and M concept would be eliminated from between the array, and you would just have these new arrays 1 and 1 and N and N. So that would be this thing. Like if there's at least one element other than the index in this range, then we can still maintain our LR array. And finally, we operate on the joker, the MM, and we can either push him to the start of the array or to the end of the array. That would correspond to the range 1, 1 and NN. Finally, once we are done with both of these things, like once we're done with all of these things, we just return a merged ranges. Like the reason we are returning a merged ranges is because there may be duplicates in our ranges, and we just basically like iterate over all LR, and wherever the ranges overlap, we just combine them, merging them into one single big range. And finally, we just get the number of possibilities. If I open my solution over here. Yeah, right. And finally, once we are done with application of our ranges, we update our ranges and we get the number of possible places where our joker card can be. To do that, that's basically like calculating the sum, sum of lengths of all ranges, that is R minus L plus 1 for all ranges. And that was problem F. Now let's move to the last problem. Max, right, there can. Yeah, at max there can be only three ranges, one starting from left, one starting from right, and one in between. So looking at the code, it may look like the time complexity can go up to n squared, but since there can be only three ranges, not n squared actually, n q squared, but since there can be only three ranges, you're actually only kind of operating on a constant number of ranges in each iteration. So the overall time complexity would be big of q, not considering anything else. Yeah. The final problem in this, like we had to play a game. The game had a field of 10 power 9 square cells, basically considered to be an infinite number of cells. And we had n snakes, and we had to place each snake into some cell. Initially, each snake occupied exactly one cell, and we couldn't place more than one snake in a cell. And after that, the game starts. And the game lasts for q second, and each q second we basically have an operation. In this operation, we are given number of the snake that can be between 1 to n. So in this operation, either the snake can enlarge, meaning that if if the snake lies from L to R, that snake can go up to L, from L to R plus 1, or that snake can shrink. Basically, if it's between L to R, it will go from L to R plus L plus 1 to R. So basically, if we were to visualize this thing, so an enlarge operation would look like this is our field. So initially, say the snake was from L to R. After an enlarge, our snake would lie from L to R plus 1. Like this would be our new snake. This was our old snake. And similarly, like shrink would be if our snake lied from L to R, then this would go from L plus 1 to R. So this was our previous snake, this was our new snake, and this is the shrink operation. And basically, we were given that for this snake S of I, either enlarge it or shrink it, and we had q such operations. And in each second, exactly one event occurs. So there are like no two or more events in any second. And what we're given is if any snake runs into an obstacle, so an obstacle is either another snake, like you had one snake and it's expanding and it crashes into another cell, like it reaches a cell where there's already one more snake, or you reach the end of the strip, which won't really happen because there's 10 raised power 9 and you're doing at most 10 power 5 operations. So not really to be considered just for sake of completeness, but yeah, right. You'll lose if either of these things happen. So the major point to be considered is what happens when you crash into other snake. You lose, so you can't crash into other snake. And if none of these things happen during these operations, you win, and your score is equal to the maximum cell occupied by any snake so far. So let's just work out what this is saying. So consider this test case. And basically, like what we have to do is we have to place the snakes initially in such a way that our score, the score at the end of this game, was minimized. Like it was minimum possible. And we could place our snakes anyway to at initially to achieve this score. So let's say this is problem, this is not problem F, this is problem G. And this is our test case. Now the most optimal placement for this test case will be actually so in the most optimal scenario, you would actually place your snake 2 over here, 3 over here, and 1 over here. First operation, snake 1 enlarges. After first operation, snake 1 becomes 2, 3, 1 enlarges. So one more at the start. in this operation, snake 1 shrinks. So this guy, like this part becomes empty, this cell becomes empty. Snake 1 shrinks. So you have an empty cell over here. And this is snake 1. In the next operation, snake 3 enlarges. So this cell is filled by 3. So our grid looks like 3, 3, 1. Next operation, snake 3 shrinks. So our grid looks like 2, an empty cell because this part has shrinked, and 3 and 1. And in the next operation, 2 enlarges. So 2 would go and enlarge. So that would look something like 2, 2, 3, 1. And in the final operation, 2 would shrink. So we would be left with 2, 3, and 1. And basically, now if you number these boxes starting from 1, 2, 3, and 4, so what's the maximum box that has ever been used? Like, what is the maximum box that we have reached? It's the box number 4. So our score is 4. According to them, this is the end of game, and our score is 4. There could have been many more arrangements, but in most other arrangements, your score would actually exceed 4 rather than being 4. Sorry, one order. Can you discuss this question? Yeah, right. Let's discuss after we are done with this question. And all right. So this was the first test case. And basically, what we had to do was we had to determine what would be the minimum score, minimum possible value of score that you could get after by placing the snakes in the most optimal way. And that most optimal way had to ensure that no two snakes collide. So for example, if you had placed the snakes say in this order, if you had say 1, 2, and 3, the first operation said enlarge 1, and when you enlarge 1 is over here and 1 tries to go to next cell, so you would have 1 and 2 both in the same cell, and this is not a valid arrangement of the snakes initially. So you'd have to arrange them either in this way. So you'd have to keep an empty cell in between them. And you could do it like one would go up to here and then one could enlarge itself. And then things would happen and finally like even 3 would enlarge itself. So in this case, the final array would look something like this. And in this case, the score would actually end up being 5. We have to find the minimum of the score. So over here, the score was 4. So the minimum score is actually equal to 4. And yeah, so that was the problem. I hope the problem is clear. And now moving on to the intuition for the problem. Okay, so and let's just look at the constraints for once. So the constraints were actually something a bit curious because the n was between 1 to 20, while the number of queries were between 1 to 2 times 10 power 5. All right. N was between 1 to 20, queries were between 1 to 2 times 10 power 5. So basically you can at max have O of Q or O of big Q log Q solution with respect to the queries, but your N is up to 20. So you can have anything like big of n 2 raised to power n or even big of n into 2 raised to power n solution. So these type of solutions would be fine, but n factorial won't do. So you can't really go ahead and just try to uh, you know brute force through all the different combination in which you can place the snakes. So that's not allowed. But something like 2 raised to power n or n into 2 raised to power n would be feasible within these constraints because 2 times 10 is around 10 power 3 and 2 raised to power 20 is around 10 power 6. And even with 20 into 2 raised to power 20, that would be around 2 times 10 raised to power 7. So that would be somewhat feasible given that you can implement it in a very good way. Now, that was about the constraints. Now, how do we even approach this problem? Okay, we can try to place things greedily, but I mean, you could just go through a few examples and you would see that the greedy approach, it's not really like, first it's difficult to even prove that if you find an approach, and in most cases for most greedy approaches you'd just find that somewhere or the other it will fail. So a greedy approach doesn't really work. And let's start with one snake. Okay, what happens when you just try to place one snake? All right, you have one snake, and to minimize your score, you just place this one snake over here. Let's just say this has starting at L. You first maybe get an increment operation, and also the operations are valid, like the snake of length 1 never shrinks, so you won't have anything like your snake of length 1 and shrink it, because shrinking it won't really be possible. So snake of length 1 never shrinks. Now you would have some operations of form, okay, expand it, then you would occupy two cells, then somewhere here shrink it, then first cell would be empty, and then this cell would be occupied, then shrink it, sorry, enlarge it, then maybe enlarge it once again, so on and so forth, and maybe shrink it a few times. And in case of a single snake, what you'll see is you start at 1, okay. If you start at 1, when do you travel to the next cell? When you increase an enlargement operation. Okay, so you're over here, you started over here. When you when can you move to the next cell? When you encounter an enlargement operation. Only when you encounter an enlargement operation can you move to next cell. When you shrink your snake, this the tail is affected, not the head. And the head decides the score. So if this lies at 3, your score will be 3. If this lies at 7, your score would be 7. And which operations decide basically what my score would be? Basically the number of enlargement operations. If you have one snake, and your score is as good as the number of enlarged operations that you have in your queries. Okay, so that was the case of one snake. So that's like, I think, fairly simple. So if you had just one snake, you place it at 1 and count the number of enlarged operations, and that would be your score. Now let's try something that's a bit more complicated. What happens when you have two snakes? Okay, what happens when you have two snakes? Well, you have two arrangements. You can either place snake 1 over here and snake 2 somewhere over here, or you could place snake 2 over here and snake 1 somewhere over here. Okay. And let's just say that the snake 1 starts from L and has a length of len, and the snake 2 starts from L2 and has length of len2. For now, just forget this arrangement. We are just only considering this arrangement. What would be the score with this arrangement? Okay. Now iterate over all the queries. If the query is for S of I equal to 1, if it's for 1, if it's enlarged, if the query is an enlarged query, what happens in this case? Well, if the query is enlarged query, the length of the first guy is incremented. If it's not an enlarged query, but rather a shrink query, if you're trying to shrink your snake, in that case, first thing, your length is decremented, and then your L, the point where your snake start, that's incremented. Basically, your enlarge would correspond to L, and this is your length. So after enlarge, you would have L, and this is your new length. And after shrink, your length would decrease and L would move from here to here. So an enlarge would do increment length, shrink would decrement length. And that would be for S of I equal to 1, and for S of I equal to 2, we can update its corresponding variables. Now the problem is, for one snake, we didn't have to deal with any collision. For two snakes, you will have to deal with collisions. Okay. When can collisions occur? Well, you are over here at L. You are getting up to this length. Your snake has this length. Let's just say that I'm counting the length without the head. So the R, the point where the snake will end, is actually equal to L plus length. So if at any point the L2, so we have L1 over here and we have this length 1 over here, and then we have L2 over here and we have this length 2 over here. If at any point the R1, that is the end of the first snake, if the end of the first snake, that is L1 plus length of 1, if this thing becomes greater than equal to L2, then we can't then we'll have a collision, because this is L1 and will go for length 1. So this snake would basically have extend for length 1 number of cells, and then you'd have actually length 1 would be starting over here, because we are considering length minus 1, so that we can represent our R in a better way. And this would be where the two snakes would overlap. And since the two snakes would overlap over here, this can't be a possible arrangement. Then the question is, how do we fix this arrangement? Is there some way in which we can fix this arrangement? Let's just say that I started my 1 over here and my 2 over here, and I want to maintain this ordering, that 1 comes before 2. So that ordering has to be maintained. And I just want to see that, okay, I have to expand, basically expand 1, and expanding 1 leads to my conflict with my 2, so they would overlap. So what I can do is, if the 2 overlaps, just shift the all cells of 2 by 1 place to the right. What we can do is shift all cells of 2 1 place to their right. And even if, say, 2 was a big snake, what we can just do is we can shift all of them 1 place to the right. And now notice that if you increment L, like if we increment the L2 of the 2, that's as good as saying that we have shifted all the second snake 1 place to the right. All the operations that have been done on the second snake have been shifted 1 place to the right. So like what I'm trying to say is, if you started with L2 equal to 1, then your all operations would be with respect to this cell. Now somewhere over here you had this, not say 1 but say 2 or 3. If you started with L2 equal to 3, all your operations would be with respect to this cell. Your snake would start over here, it would expand, contract, and reach somewhere over this cell. Okay. Now let's say during some operations, your L1 actually started to overlap with the second snake. Now to remove this overlap, you did the most obvious thing. You incremented L2. What this corresponds to is, every operation that you have done on L2 would actually shift 1 place to the right. Okay, so this is like shifting 1 place to the right. And basically, like in this way, we can just start with L1 equal to 1 and maybe L2 equal to 2. And initially, let's just say that length 1 equal to 0 and length 2 equal to 0. And go on operating, doing all these operations on them. Like operations in the sense that if you want to enlarge, then increment the length. And if you want to shrink, then increment L and decrement length. And if at any point there's collision between the two snakes, in that case, increment L2. This is incrementing L2 is as good as saying that instead of starting with L2 equal to 2, we started with L2 equal to 3. One more increment, instead of starting with L2 equal to 3, we started with L2 equal to 4. So basically, like this would allow us to avoid all the collisions and get the answer, like get the minimum score that we would have by placing snake 1 before snake 2. And we can also do it vice versa for snake 2 and 1, and the minimum would be our minimum score in case we had 2 snakes. Okay. So in case we had 2 snakes, that would be the answer. Now what happens when the number of snakes is greater than 2? Okay. So up to 1 and 2 snakes, we have some form of answer, and we are actually going to use that for solving the general case. What happens when you have greater than 2 snakes? Well, the first thing is that if you don't have any greedy solution, there are n factorial starting positions to consider. Okay. There are n factorial starting positions to consider, like you could place 1, 2, 3, then you could have 2, 1, 3, and you could have 3, 2, 1, something like this, like overall n factorial positions to consider. And even after you have these n factorial position, you still would have to consider one more thing, that what would be the spacing between these snakes. And after that, you can just go over all the queries and calculate your final score and take the minimum of that. But since n is less than equal to 20, 20 factorial is a very huge number. So you can't have n factorial over here. Now, notice that let's just say you have placed the first snake. After some places, you have placed the second snake. And after some places, you have placed the third snake. All right. And after performing all the operations, your third snake goes up to this cell. All right. Now you're trying to place your fourth snake. Okay. What you're trying to do is you're trying to place your fourth snake. Is my placement of fourth snake dependent on my placement of 2 or placement of 1? I've already placed 3 in the best possible cell, which will minimize my score as much as possible. Now, when I try to place 4, it doesn't really depend on 2 or 1, because you see, the moment you say that 3 has been placed after 2 has been placed after 1 and 3 has been placed after 2, it means that no matter how 1 or 2 expand or shrink, they are never going to cross 3. So you can never have 2 over here, because 2 can never cross 3. So when you try to place 4, you only need to consider the value of 3 for this thing. And if you see where this points to, this is basically pointing to, let's just ignore the rest of previous array. Let's just say it has a length of L, and you basically need this much space for all these 1 and 2 to expand and shrink. And say that you're starting a new array with 3. You have placed 3 at the start of the array. And what's the best possible way to place 4 such that you minimize the score? Okay. What's the best possible way to minimize to place 4 such that you minimize score? And forget about how we came up to 4. We'll discuss that later. And if you look at this problem now, this is basically just the problem that we faced with, I guess, yeah, over here, like with placing 2 snakes. When we were placing exactly 2 snakes, this was the problem that we faced. And with our 2 snake analogy, we could calculate the L1 and length 1 and L2 and length 2, and L2 corresponding to the start and length of the snake with value of 4. And finally, our answer would be basically what is this length L over here that you have to offer before, plus what would be your L2 plus length 2, that is the length of snake 4, up to where will it extend. That would be your score. And if you actually look at what does this add to our score actually, what is the cost of adding 4? So before this, we had this 3, and this 3 was up to L1, and it traveled at max up to length 1. And when we added this 4, so we added this 4 somewhere over here, say. This was up to L2, and this traveled at max up to length 2. So initially our score was this previous X, whatever array we had, our score was x plus L1 plus Len1. And after adding 4, our score became x plus L2 plus Len2. And we can just take the difference, and the cost of adding 4 is actually this thing. So that's how you can basically, given that you have an array and you have placed some number of snakes, you can calculate what would be the cost to add a new snake s dash. And now if you go through all these things, finally you have left with, like, if I have placed 1, 2, 3 and say 5, and I want to place 4, what I do with 4, the answer, how 4 changes my answer doesn't depend on 1, 2, or 3. It only depends on the last snake that was placed. So the change in answer due to addition of 4 will only depend on the last element that was placed, not all of these elements. And if you kind of look at the whole thing, it's actually pointing to a solution where we basically maintain masks of the snakes that have been placed. So we can maintain the mask saying that of, say, 1 raised to power n, like n size integer, where the ith bit will say that has ith snake been placed? Like, have you placed the ith snake? And along with this mask, you will also have an element I such that all snakes in mask have been placed. And the last snake is I. Okay. And if you want to go from mask and you want to place another snake J into this whole mix, then you could just, like, add this J into mask by ORing it with 2 raised power J. And the increased cost would be cost of placing I and J parallelly, basically the cost that we calculated when we just tried to place only 2 snakes. So some off topic, yeah, right. I don't think there are any doubts. This is like slightly a bit complicated. So, all right, like, let's try to move to the code, and we'll see if there are any doubts, do ask them in the chat. But the overall idea of this problem is we maintain our DP state, that is mask and I, which basically says that what's the min score given that we have placed all snakes in mask and I is the last snake. Okay, so that's the, like, core idea of the dynamic programming. Like, that's the DP state, and the transitions would be look something like you are at this mask I, and this was the last state, and then you go to this mask I and or 2 raised power J, or it with 2 raised power J, and the new ending snake is J, and you can basically calculate the cost of going from I to J with the above formula, like the ones we derived for the snake case. And yeah, like, one more thing, like the optimization. If you actually look at calculating this cost part, there can be at most n squared ij pairs, and calculating each of them can take at most big of q because you have to go two operations. So, and the DP states, like, there are going to be big of 2 raised to power n masks, and each of them will be associated with a final element. So 2 raised to power n into n. Now, if you actually try to calculate this thing on the fly, then your overall time complexity would end up becoming 2 raised to power n into q, and this won't pass. Like, this in itself would become something like 10 raised to power 8, and this would add additional 10 raised to power 5. So what you can do is we can just calculate this thing, because n squared is n is up to 20. So n squared is up to 400, and q is around 10 power 5, so n squared into q would give you something around 4 into 10 power 7. So that would be the time complexity, and space complexity wise you would have some 400. So we can just pre-calculate this thing and make the whole transition work in big of one time. So, and yeah, like each of these transitions, so the total overall time complexity would actually end up becoming something like big of n squared 2 raised to power n, and the space complexity would be big of n into 2 raised to power n, because each transition goes to n different g. If I were to go the code, this is just the solve function. First, we take the input n and q, and we input all the q operations. Now, what we are doing over here is we are storing the operations, like what are the operations that are done for the ith snake. And if it's ch, like we store what is the index or the time where this operation was done, and whether it's an expand or contract operation. So this is what we do. Then we pre-calculate the cost. Basically, what cost ij says is, I have already placed my snake I, and I have whatever the minimum score that I get by placing snake I. And now I want to place snake j in front of snake I. What would be the extra cost? What would be the increment in the score that I'm going to get because of placing this j? And if I and j are not equal, basically this is similar to calculating the cost for exactly two snakes. If I and j are equal, cost of I to I, that's like calculating the cost for a single snake. And yeah, like this is the cost for calculating the single snake. Basically, it's just the number of increment operation, the number of expand operations. And if we consider the cost for exactly two snakes, first thing we do is we merge the two operations. So this part, basically we are just taking both the operations for ith snake and jth snake and merging them into an array and sorting that array. Then we start by placing the first snake at 1, the second snake at 2. We go over all the operations sorted by time. So we do the operations as they come to us in according to the question. Now, if the index operated is I, then if it's an enlarge operation, increment length. If it's shrink operation, increment L and decrement length. Similarly, if it's the other index, if the L1 plus length 1 is equal to L2, basically what happens if the first snake goes on and intersects with the second snake? In that case, basically shift the whole second snake one place to the right, and that would basically shift all the previous and current and next operations one place to the right and remove the overlap. And finally, like initially with just the first snake, this would have been our number of the minimum score. With the second snake, this became the score. So what is the extra score that was added because of the second snake? That's the difference between these two. And this is like our infinite. And finally, we just go on and have our DP state. So for DP state, initially what we say is for each of the snake taken individually, this is our cost I to I. Like this we calculated over here, basically number of enlarge operations. And then we iterate over all the possible masks, like from 1 to maximum mask, that is up to 10 power n minus 1, 2 times 2 raised to power n minus 1 mask. Then for each mask, we iterate from 0 to n. This basically checks, is this snake present in this mask? Okay, if this snake is present in this mask, then basically we are considering the pair mask and I, saying that I have I have placed all these masks, and I is the last snake that was placed. And then we iterate over all the snakes J which are not in mask, and we try to add them to the mask. When you add J to the mask, like the new mask will be mask and or of 2 raised to power J, that is one shifted left by J places. And the new mask ending with J, its minimum score will be what it already was, which is initially set to infinite, and what the score of the previous mask ending at I was, and what would be the extra score that you would need to add when you place J in front of I. That's basically parallel to kind of calculating the answer for two snakes. So this would be the overall loop. The outer loop would run in 2 raised power n, this would run in n, this would run in n. So overall it would be something like n squared 2 raised power n. And like given the constraints n up to 20, 2 raised power 20 would be around 10 power 6, n squared would be around 400. So n into 2 raised power n would be around 4 times 10 raised power 8. So yeah, like depending on implementation, this would pass like 10 raised power 8 operations. You could do that in 1 to 1.5 seconds. And finally, we just set rest to infinite initially and see for each 0 to n, what is the minimum score that you would get by max mass minus 1, but this is 2 raised power n minus 1 by considering all the snakes and the last snake being I. So the rest would be minimum of all of these. So, right, that was this. Now, to code it. You need to code it. I don't really get what is. But yes, like these were the A to G problems. So are there any doubts with regards to the problem G? All right, I guess that's was problem A to G. And yeah, like thank you for attending the PCD.